Welcome to the journey. This will be a journey through time, but not forward in time, not backward in time, but deep in time. We're going to go to shorter and shorter intervals of time and see what happens at all in such brief moments. How do we organize this? Well, imagine that you have a magic tool that allows you to slow down the passage of time 100 times, 1,000 times, 1,000,000 times, 1,000,000,000 times. You just press a button and the passage of time slows down, and you stand there and watch this all going on around you. Is that what you would then see in the world around you? What processes that you don't have time to notice normally would you see? In general, this question is very funny because it's like an excuse for science fiction writers to write a book or make a movie. And in general, in popular modern movies, there are sometimes superheroes who can slow down time, for example, like the X-Men, and then in that slowed down time, they're out there doing something. The funny thing is that science, in a way, can do that too. Of course, it doesn't know how to slow down time, but it has the tools to track super fast processes and then show us how it all evolved. And so, by studying processes of various durations with the help of these tools, we actually dive into how our world functions on the smallest, most fundamental scale. And that is the journey that we are going to take with you today. We will imagine 1 second as a matryoshka doll with smaller time intervals. Milliseconds 1,000 times smaller, microseconds 1,000,000 times smaller, and so on. Here, we'll talk about them first, then we'll take 1 second and open it up. And it has even shorter time intervals in it. We'll deal with those, and so on. So, milliseconds and microseconds. The most important thing about milliseconds is that they are quite human time intervals. Actually, 1 second is a very big interval of time. It lasts, and we feel it. You see, for example, the tenths of a second ticking away. You have time to track it. Sometimes 1 second is even too long a period of time. I'm sure none of you are capable of jumping up and staying in the air for a second. There are very few people in the world who can do that. You can say a few words in 1 second. You can declare your love in 1 second. You can do a lot of things in 1 second. And if you are doing something complicated, say playing the violin or the piano, you have time to make a lot of coordinated movements in 1 second. So tenths of a second, even hundredths of a second, is a perfectly natural human timescale. Moreover, if you go into milliseconds, right, in a matter of milliseconds, of course, you no longer have time with your eye to notice what happens in a matter of milliseconds. But such movements, such phenomena, they are all around us. It's just that maybe we haven't thought about it. Let's say you took a tennis ball and threw it against the wall. You caught it. The whole process took half a second. You caught it in time. But you realize that at the moment when a tennis ball hits the wall, it does not bounce back instantly. It first squirms, stops, and then flies off. And this process, it also takes some time. The question is how long? It's clear that it's short, and it is clear that we do not have time to notice it with our eyes. But how long? Here's the funny thing is that you don't actually need to be a physicist or a technician to calculate this. You can estimate by a single formula, a very simple formula that you know very well. It's the formula for uniform motion. Speed times time yields distance. If you know the distance and you know the speed for some reason, you divide the distance by the speed, you get the time. And that's almost always enough. The process itself can be very complicated, but we don't need to calculate it honestly. We only need to get a sense of the scale of the times, and that formula is usually enough. Let's see how it works. Here's when we throw a ball with all our might. Then you throw it at a few meters per second, maybe 10 meters per second, maybe 20. The important thing is that the scale is on the order of 10 meters per second. When the ball flies up against the wall, it flattens, of course. How much flattens? Well, a few centimeters. That's enough for us, too. We don't need to know the exact numbers. And then you divide one by the other. It's a funny formula. A few divided by 10 meters per second. You add up the numbers, you get a few milliseconds. That's a phenomenon that lasts only a couple or 3 milliseconds. And that's everyday life. Of course, this whole thing can be captured on an ultra-fast camera, and you can see how it all unfolds over time. You can see how many milliseconds it takes for a ball to bounce. There's the first touch, there's the return, So it takes about 3 or 4 milliseconds for a tennis ball to bounce. It's not an instantaneous process. You can do the same thing for a ping pong ball. There, of course, the ball deforms less. That's why the impact is faster, but it still takes some time. People have studied this, physicists and Chinese physicists, because ping pong is very popular there. And they got about half a millisecond, also an everyday phenomenon. In the world around us, there are other phenomena in the millisecond range that you can see with your eye. These are flickering LEDs. In general, there are many LEDs in the world around us now. Some of them shine continuously, some of them flicker with high frequency. If you look directly at them, you won't notice the flickering. Here's a look at this clock. This clock is flickering. It's flickering 200 times a second. Can you see that it's flickering? To see this, you need to photograph the flickering object, not just statically, but at the moment of photography. Turn the camera sideways or from top to bottom. It doesn't matter. The main thing is to turn it. And then what is flickering, you will leave such dashes on the image, a dotted line. And if something is shining continuously, it will be a solid strip. Here is a picture of a dressed-up Christmas tree. Just take a picture of the Christmas tree with a regular camera, turning it around, and you can see that some of the lights are twinkling, and some of them are glowing continuously. So it's all around us, we just don't usually notice it. The question is, at what frequency? To do this, you need to take your camera and set a certain shutter speed. Let's say you set it to 1/100th of a second. You turn it around and count how many strokes you have in that image. And through that you calculate the flicker rate. Here's a couple of examples. Here, so I was taking a picture of my microwave indicator, rotating from top to bottom. Here I set the shutter speed to 1/25th of a second, and I see that I got 6 images in 1/25th of a second. So that works out to be 6 times 25 equals 150 images in a full second. When you just look at the microwave, you don't see that. But with a camera, bang, you can measure it right away. Something similar you can see with your own eyes, without smartphones, without cameras, without instruments. You just need to practice. How do you do that? To do this, you need to look at the shimmering object not directly in front of your gaze, but by swiping your gaze back and forth. At first, of course, you can turn your head, but then it is better to look back and forth. And having practiced, you will be able to see fast flickering objects, even if their frequency is higher than kilohertz, more than 1,000 times per second. Say, often the tail lights of a car, they flicker too. If you flick your eyes back and forth, you'll see something similar. There are smartphones that allow you to shoot at a high frequency. Modern smartphones usually give you 240 frames per second, but in general there are some models that give almost 1,000 frames per second. If you have such a smartphone at home, a great opportunity to see what is going on in the world around you. This in itself is cool, that with the help of simple devices, you can look into the place that people usually do not see, and you do not need super expensive tools for this. Moreover, there are phenomena that can't even be tracked with such smartphones. For example, a well-known problem, you take a spaghetti, carefully bend it, not clamping it hard, but just holding the edges, and at some point it bursts, and it breaks as a rule not into 2 pieces but into several. This famous problem bothered people 100 years ago, physicists at least, because it's really an incomprehensible process. How is it that several faults appear at the same time? Why do they appear at the same time? What's happening there? Here are 2 consecutive frames. On the first frame, the spaghetti is still intact. On the second frame, everything, already several fragments. Here they are flying. So this whole cascade of fractures happened within 1 millisecond. It takes a few tens of microseconds. These are all home experiments, you know. Why microseconds? Actually, because you can also calculate by that formula, the formula of uniform motion. The typical velocities of elastic deformations in solids are hundreds of meters per second. They may vary from substance to substance, but it's of that order of magnitude, and the pieces are a few centimeters in size. If you divide one by the other, you get that through elastic waves, different parts of the spaghetti sense each other on a scale of tens of microseconds. So if you want to really figure this out, you need a super fast camera. already a smartphone won't do, that gives you tens of thousands of frames per second, preferably hundreds of thousands, so you can actually track everything. Physicists have done this experiment. Here's the first spaghetti fracture, here's the second spaghetti fracture. They didn't really happen at the same time, one after the other, but the time difference between them is about 35 microseconds. And this is a normal, everyday occurrence. Okay, let's go a little bit deeper. So we've worked out with you that the millisecond and the microsecond are actually everyday life. Now let's dive inside 1 microsecond. So 1,000th of a microsecond is called a nanosecond, and 1,000th of a nanosecond is called a picosecond. It would seem like these are insanely short time intervals. Nothing is moving at these time intervals anymore. But let's check it out. What manages to happen in 1 microsecond, we already understand in principle. Take, for example, a bullet that flies at a speed of 1 kilometer per second and see how much it has moved in a microsecond. Multiply a bullet 1,000 meters per second by a microsecond and you get 1 millimeter. So if you had time slow down 1,000,000 times, such a supersonic bullet would fly very, very slowly. You would only look closely and see that it was moving. Here, for example, is a video shown here. Maybe you don't notice, but it has already started to move. The ball that's flying at high speed is about to hit the glass. Here it's hitting the glass, here it's cracking, so you can actually see something on microseconds. The cracks are scattered on microseconds. Because this cracking of the glass, when a ball hits it like this, it is already going at a speed of kilometers per second. This is a real video taken by a camera at 10 million frames per second. That's why it shows you for every second of this video about 3 microseconds of real time, so you have an idea of what's happening in microseconds. Basically, something is moving. Let's go even deeper into time now. That is, let's multiply these, say, 4 kilometers per second. This is the speed of sound waves in glass. By a microsecond, we get 4 millimeters, a microscopic distance. Now multiply that by a nanosecond, 1,000 times less. We get 4 microns. This is a very small distance. You can't see it with your eye. But if you have a microscope, you will see how in nanoseconds the crack will grow gradually deep into the glass. That's what you'll see. If you go to picoseconds, in 1 picosecond the crack will travel only 4 nanometers. Or if you go to atomic units, 40 angstroms. That's atomic units. You can't see that in a microscope. You will only feel it if you start modeling it all at the atomic level. That is, in a time of about a picosecond. Modeling shows that the rupture inside the glass will advance by about that much. So this is the scale on which this whole thing will move, in a picosecond. And here you probably already realize that by talking about picoseconds, we are moving to the molecular time scale. That's it. There is no point in talking about objects. On the picosecond scale, it makes no difference whether your body is liquid, solid, gaseous, what shape it is. It doesn't matter at all. On such scales, we are talking about the behavior of individual molecules or atoms. Here's another example. Here too is a modeling of a cluster of water that crashed into a wall at a speed of 3 kilometers per second. Here is the counting of times here going 1 picosecond of simulation for 1 second of real time. Here's a typical scale of times and motions on the size of individual molecules. This is how you would see the world if you used a magic machine to slow down the flow of time by 1 trillion times. Here's another video to give you an example. How water crystallizes when heat is removed from it. That is, how water freezes. Here you see the part that's already so crystalline. That's ice. There's more water here. Molecules move back and forth, rearrange themselves somehow. And gradually, if you take energy away from them, they gradually start to fit into this crystal lattice. Not instantly, over many tries, but sooner or later they finally form ice. Now this whole video that just happened here took about 100 picoseconds of modeling. So, at nano and picoseconds, there is, though, some type of motion that has something to do with the macro world, which is our everyday scale. This is the motion of light. Here's an example. Sequential shots of a short pulse of bright light being emitted by a source, reflected off mirrors, and then traveling back to the source. So the time difference here is about 1 nanosecond, and you can see the light beam moving, And why is it traveling so fast? Because it's fast. This is the speed of light. 300,000 kilometers per second. The same speed of light can be expressed a little bit differently. So 300,000 kilometers per second is the same as 300 kilometers per millisecond, or 300 meters per microsecond, or about 1/3 of a meter per nanosecond. The same thing can be seen in dynamics. So people have actually videotaped this. Here's a look at how you would have light propagating. That's where the nanosecond counts down. Here's where it's reflected in the mirror and flies back. Actually, of course, it's not really a real video in the usual sense that we shoot in a single span. It's some synthetic image of many repeated experiments, but the result still looks impressive. Since the speed of light affects not only the travel of light, but also the frequency of electromagnetic oscillations, we have another clue between these nanoseconds and picoseconds and the usual scale of distances. These are electromagnetic waves and their wavelengths. Time can be converted to frequency. So if you have, say, a period as 1/1,000,000th of a second, that means you have a frequency of 1,000,000 times a second. So megahertz, then gigahertz, terahertz, and so on. 100 megahertz are the typical waves we listen to. Music, radio, and so on. They correspond to a wavelength of about 3 meters. Why do we listen to this frequency? Because it's more convenient to emit. You just take a macroscopic antenna of ordinary human dimensions and you radiate these 100 megahertz. It's no problem. If you want to go deeper in time, that is, by raising the frequency, you inevitably have to reduce the size of the radiators and receivers. For example, a microwave also has a standing wave, an electromagnetic wave. It has a standard frequency of 2.45 gigahertz. The wavelength is 12 centimeters. So when you heat something in the microwave, of course you don't see these radio waves, but they are there. And so they have this wavelength right here. So they stand there and they oscillate. Basically, because of their tremendous speed, light and any electromagnetic waves allow us to bridge the gap between picoseconds and nanoseconds and the everyday scale of distance. Perhaps the last point in this story is, maybe a little bit unusually, how this assessment of frequency and time relates to the internet, to the speed we're used to. Here's a look. Suppose you have a Wi-Fi router. It's transmitting data from a cable to your computer wirelessly. So it emits some kind of radio wave with a certain frequency, and this wave is caught by your receiver and receives information. What is that wave? If it's just a boring wave like that, you're not going to transmit any information. In order to transmit information, you need to change this wave a little bit periodically, modulate it. You can modulate it in different ways. There is frequency modulation when the wave first goes a little thicker, then a little less, then a little thicker. That's how you transmit bits, 0, 1, 0, 1, and so on. You can also use amplitude modulation, where the wave goes at the same frequency, but just sometimes stronger, sometimes weaker, stronger, weaker. It's common to use frequency modulation because it's robust to noise. So in order to encode even one bit, you need at least a couple of oscillations, at least a few oscillations. And now let's imagine how the speed of information transmission depends on this carrier frequency. If you have a carrier frequency of an electromagnetic wave of 1 kilohertz, that is of course very small. So 1 kilohertz means 1,000 vibrations per second. Let's divide by 6 to use 6 periods for 1 bit. We get 160 bits per second, which is 20 bytes per second. That's very little. It can only be an SOS signal you have time to send, and that's it. Actually, people work at this frequency when they communicate with deep-sea submarines that swim deep in the depths of the ocean. They cannot receive high-frequency radiation because the water prevents them, but low-frequency can. So communication with these submarines is through very low-frequency vibrations, and they have such a communication channel, they transmit a few bytes per second, no more. So for us, of course, it's unacceptable. Okay, raise the frequency to 1 megahertz. Instead of 20 bytes per second, we get 20 kilobytes per second, but it's still inconvenient. 30 years ago, maybe the internet would still fly at these speeds, but now it's not enough. So you need to go from megahertz to gigahertz? Only then the speeds will be serious, tens of megabytes per second. That's the internet speeds we're used to. And that's why it's a funny conclusion that if you want to use the internet at the speed you're used to, you inevitably need a router that works at gigahertz frequencies and higher. That's why the typical Wi-Fi routers that everyone has, they typically operate at these frequencies, 2.4 gigahertz or 5 gigahertz. The 5G standard is already going further. Now at least, the Chinese are developing 6G, and they're talking about tens of gigahertz. And they want to transmit gigabytes per second over this wireless connection. Anyway, it's a funny connection between the internet that we're used to and the gigahertz time period, which is further converted into picoseconds, if you will. Right, well, let's move on. So, picoseconds. Picoseconds are small intervals of time, but we now take a picosecond, open it up, and inside a picosecond we have femtoseconds, and inside a femtosecond we have attoseconds. And we dive into them. Let's get a sense of what's even happening at these scales. Imagine molecules that are moving somehow on different timescales. They move slow or fast. A picosecond is roughly the watershed below which, that is, faster than which molecules are already standing. And on larger timescales, molecules are already lubricated into collective motion. That is, if we're talking about nanoseconds, the molecules are already flying fast, and we can already talk about collective motion like ultrasound or something like that. If we talk about picoseconds, we see individual molecules, that they are flying and colliding. If we go deeper, and we talk about femtoseconds, all the molecules have already moved nowhere, they are creeping slowly, and it's clear that attoseconds, all the molecules are already standing. At attoseconds, the molecules are already stationary. Everything is stationary in the surrounding world except the electrons. So a picosecond is such a big watershed between two worlds, the world of individual atoms and life inside atoms, and the movement of matter that makes up macroscopic motion. Let's just estimate what happens to matter in 1 femtosecond. A femtosecond is 1,000th of a picosecond, or 10 to the minus 15th power of seconds. Let's take one molecule. During this time, the molecule manages to move a small distance much smaller than its size. The movement of molecules on the femtosecond scale is no longer visible. And so it doesn't even matter what kind of body the molecule was from, or even what aggregate state it was in. Liquid, gas, solid, it doesn't matter. It just won't move in a femtosecond. But for femtoseconds, or rather for tens of femtoseconds, molecules have time to oscillate. That is, if you slow everything down 100 trillion times so that 1 second of your perception corresponds to 10 femtoseconds of the real world, then during this time you will see that the molecules may not move, but they have time to oscillate, because the oscillation periods are typically tens of femtoseconds. And the most important thing on this time scale is you suddenly notice that in matter, especially in metals, there is something other than atoms. There are electrons, and they're very fast. Electrons are light, so they're fast. So, while the molecules are flying back and forth, inside the metal, you have electrons, free electrons inside the metal, flying fast and fast among these ions. They live on the femtosecond scale. This is an interesting boundary because here we begin to feel how, in fact, chemical reactions take place on the scale of individual molecules. We study chemistry in school, a formula, this molecule plus that molecule results in this molecule. Okay, but it's a written formula. How does it happen in reality? Imagine you have one molecule, another molecule. They love each other for some reason. And so when they fly towards each other, something rearranges itself, reconnects, and then they fly away. How long does it take for this single act of chemical reaction to take place? Typical time is in the order of approach time and departure time, unless, of course, they need help. It's probably the fastest reaction there is. As they approach, it's 1/10 of a picosecond movement. While they're flying inside each molecule has its own electrons that are sitting there, not moving anywhere. because they're already moving too fast. They're already in clouds, in these electron clouds, holding the atoms together into one molecule. And then when these two molecules get close enough to each other, on the order of an atom away, the electrons suddenly start to feel these electrons connect. Because there's a chemical bond between them, the rearrangement of the electron clouds begins. And this all happens quite quickly while the molecules are flying up. This rearrangement of electrons happens in femtoseconds. The molecules are moving very slowly during that time. So for each position of the molecules, the electrons already have time to adapt. And when the molecules fly up and realize that now the electron clouds they are told to split into other molecules, the molecules say, okay, we'll split into other molecules, and gradually split up. This single act of chemical reaction takes about 100 femtoseconds. There are no chemical reactions faster than 100 femtoseconds. 100 femtoseconds is about the fastest reaction, and because it all lies in the femtosecond range, the study of these chemical reactions has been called femtochemistry, because we're really studying the essence of how a chemical reaction occurs using the femtosecond scale. Ahmed Zewail was once awarded the Nobel Prize in Chemistry for developing femtochemistry methods. He is a researcher of Egyptian origin. He did his main work in the United States, but in Egypt he is very much loved and remembered. In his honor, there are whole cities named after him. Anyway, he was a cool man and he developed a lot of things. It's interesting that some chemical reactions, which are biological processes, also take that amount of time, and this research was called femtobiology. So those rare processes that take time in the range of hundreds of femtoseconds, which are important for example, vision or photosynthesis, they are all also studied by these same methods. Imagine vision. What is vision? We see light. We're going to break that down into separate acts now. What does it mean that we see light? Well, a quantum of light, a photon, flew into our eye, reached the retina and hit the retina. The photon was absorbed by some molecule. Our retina is filled with light-sensitive molecules, which start to deform somehow when hit by light. That is, in the end, after the photon hits, the molecule must generate an electrical signal, which will go along the nerve to the brain. That's kind of at the end. It's a long process. How does it all start? How do you know what it means that a molecule has absorbed light and started some process? There is a certain complex molecule, rhodopsin, which, when absorbing light, suddenly in a certain place of this molecule, between 10 and 11 carbon, the electron cloud is rearranged. And as a result, the molecule from this state is rearranged into this state because it is energetically more favorable. So this first process of light absorption is fast. It's a femtosecond. And further reconfiguration of the molecule and changing its shape takes hundreds of femtoseconds. And after the molecule has been reconfigured, it starts to interact differently with neighboring molecules in its own space and starts to excite them and transmit an electrical signal. That's how vision begins. That's how photosynthesis begins. And this is all on a scale of less than a picosecond, which is hundreds of femtoseconds. That's why it's called femtobiology. How can people see this stuff? It is clear that no super-fast cameras, still cameras, video cameras are already here. It is impossible to do, and it is not necessary, because we will not be able to look into individual molecules, and we will not be able to shoot frames with such a frequency. We need something else. This something else is a method, which is probably the most important method in general in the whole physics of fast processes, called the pumping and sensing method. What is this method? It's actually a simple idea. It's just carried over into atomic physics. Imagine that you need to film some process. For example, a drop of milk falls, for example, on a table and turns into a crown, like this. Of course, if you have a super fast video camera, you can take it and film it, no problem. But what if you don't have that? Okay, let's say you just have a camera and a flash. And then if you flash at the right moment in time, you'll see the state of the system at that moment in time. And now all you have to do is just repeat this experiment time after time and flash at different moments in time. Of course, it's going to be different experiments. But if you have conditions that are repeated, then you would expect the developments to be repeated as well. And so this shows sequential footage of how that process happens. Now, something like this is also used in ultra-fast physics, but instead of a flash, people use ultra-short laser pulses. These are the ones that allow you to look into the femtosecond range. Here's an illustration of what happens, how the pumping and probing technique is used. First, you have a laser that generates two very short pulses of light, and they're synchronous, meaning they go right along with each other. One of them is stronger, it will hit the target and start some process. The second one is weaker. It is like a flash. It will photograph the state of the system at the right moment in time. These two synchronous pulses go, then the weaker one goes through a special delay line that we can adjust, and it is slightly delayed in time by some time 1 picosecond, 2 picosecond, or half a picosecond. And this pair then still synchronously, but with a time delay, hits the object. So you have an object, let's say a molecule. Here it sits in its calm, motionless state. The first pulse arrives, a powerful pumping pulse. It hits the molecule and starts some process. It starts to vibrate. And then, after some time, a short light pulse arrives again, a weaker one, which does not destroy it, but is simply reflected, and we fix it. And now it carries information about what state this molecule was in at the right moment of time, which we can control and tune. And now you just have to repeat just this experiment many times with different times and overlay the frames on each other and get a video. So here, let's say you have some kind of optical system. There's a molecule inside. If you shoot at the molecule, it starts to oscillate, and you want to see how that happens. Okay, we do experiments like this. So first we send a pulse that hits it, and then we send a pulse that reads it. First, they're almost simultaneous, and we get the first frame. Then, with a slight delay, we get the second frame. Now, the delay is greater. We get the third frame. The delay is even greater. We get the fourth frame. And like this, repeating these frames one after another, we get a kind of animation. That's how the pumping method of sensing works. So, it's all good as long as we are inside the frequency, inside the period of electromagnetic oscillations of light waves. Light waves, electromagnetic oscillations in general, are a very broad spectrum. Here we have the visible range. There are microwaves, radio waves, there are X-rays, our favorite. There are even higher frequency rays. If we work with an ordinary laser, with an optical laser, or near-infrared or ultraviolet, we are talking about periods of oscillation on the order of femtoseconds. You can make a short pulse out of those femtoseconds, but you will still have that pulse with a duration of at least a few femtoseconds, maybe 10 femtoseconds. You will not be able to make a shorter light pulse from femtosecond period, because then the frequency will be different, and it will not be visible light. So with all this method, you can of course study how molecules collide with each other, because they collide longer than femtoseconds, but you cannot look inside atoms, because electrons inside atoms move faster than femtoseconds. You need a different tool. You need a tool that allows you to make pulses much shorter than femtoseconds, and you can't do that with optical lasers. People realized this almost immediately after they invented lasers in the 60s. By the 80s, they had already reached such pulses and realized that it was unrealistic to go any further. And for 20 years, they tried to break through this femtosecond barrier, to come up with methods of generating very ultra-short pulses. And in the neighborhood of 2000, they were able to do it. It's a very beautiful process in itself. This process, I think, is fascinating in general. Imagine people with previous experience understanding how difficult it is to make pulses compress, how difficult it is to synchronize pulses with each other. Rubbing their hands together, they begin to think, man, now we have to get a very ultra-short pulse, much less than a femtosecond, and it is desirable to synchronize it with something else to do experiments. And so they tried to do something with atoms and realized that the atoms were doing everything for them, and they realized that atoms do it all at once, all these stages for them. How does it happen? They take atoms, say rubidium atoms, as long as they have more or less free electrons on the outer shell, and they send to these atoms a flash of infrared light long enough. This light is very intense, so the electric field inside this flash is strong, and it starts to shake this electron inside the atom. So you have an atom, its electron in a normal state, it sits, and here comes a powerful infrared flash with its own electric field. This electric field starts to drive this electron back and forth. Normally, this process would go away, but if the electric field is very strong, it can rip the electron out. This electron is being ripped out of the atom because there's an electric field that's pushing it. It tries to fly away, but then the electric field changes. It says, "Go back," and it goes back. And during both periods of movement, it accumulates the energy of this electric field. And going back, it hits the parent atom, and at the moment of hitting it, it has a high probability to sit back in its state and release an ultra-short flash, which symbolizes that I sat there. And this process is very fast. This process is much faster than this electric field fluctuation that comes in here. And at this moment, it emits a flash of light, which is no longer light, but X-ray or distant ultraviolet, which is also synchronized with this flash, flies in the same direction, absolutely, and has the same polarization, if necessary. That is, when we prepare it, we launch a powerful infrared flash into a cloud of atoms, and at the output, we get a powerful infrared flash plus ultra-short pulses that hit at the right moment. And further, this system, which nature has prepared itself, you can direct at your target and study, for example, what happens inside an atom when you excite the atom. That's what people won the Nobel Prize for 2 years ago. 3 physicists. They were really one of the pioneers. In the 80s and 90s, they developed gradually this technology, and in 2000, it started working. So let's move on. It would seem like where to go next. We've already expanded time incomprehensibly enough. We now take one attosecond and split it into another 1,000 parts. That's called a Zeptosecond. And then another 1,000 parts is called a Yoctosecond. 3 years ago, that would have been the end of it. But in 2022, physicists thought, shit, we need even less, and officially introduced the new prefixes Nanoseconds and Quectoseconds. Let's first think about what can happen on a scale smaller than an attosecond. On a scale of attosecond, all molecules are already standing, all atoms are standing. Electrons, well, maybe, move a little bit. And if we reduce the time by 1,000 times, electrons stand up in atoms. What happens at all on these Zepto and Yoctoseconds? Something is happening, but only deep inside the atoms. That's where nuclear physics comes in. So the thing is that the nucleus, it's very small. It's 100,000 times smaller than an atom. And if even light travels a distance inside the atom in an attosecond, then inside the nucleus the same light can travel in tens of Yoctoseconds. That is why this is the typical scale of the fastest nuclear transformations, with atomic nuclei or with elementary particles, which do not exist in nuclei but in principle can be born or decay. That is, we can introduce such a concept as a typical minimum duration of any nuclear reactions. It is of the order of 1/10 of a Zeptosecond, or about 100 Yoctoseconds. This is the time for which protons and neutrons inside the nucleus conditionally have time to go back and forth, or for which two nuclei, having collided with each other, have time to join and begin to separate. Unless, of course, there are no mechanisms that delay this process for a long time. Of course, in the quantum world, there are also some obstacles for processes that can significantly prolong some decay or reaction. If the fastest processes happen in Zeptoseconds, the longest ones can last billions of years, can last even longer than the lifetime of the universe, because there is some effect that delays them. Here's for your interest, the lifetime of some unstable isotopes of helium. So helium, it contains 2 protons, and it can also contain neutrons. Normal helium is helium-4. 2 protons, 2 neutrons, alpha particle, very stable, it always lives, it doesn't decay. If you add more neutrons to it, it's a heavier isotope of the same helium, and it's already unstable. It will decay after a while. Now, let's imagine that we start adding neutron after neutron to this alpha particle one by one. So we add just 1 neutron, we get helium-5. Helium-5 decays instantly, in less than a Zeptosecond. That's the typical nuclear time. This alpha particle just can't coexist with a neutron, they fall apart immediately. But if you add two neutrons, then the alpha particle says, well guys, okay, sit next to each other, and you get some neutron shell around this alpha particle, and it's basically quite long-lived. It decays. This is the kind of nucleus that decays. But the lifetime is almost a second. So by adding one extra neutron, we've lengthened the lifetime of an unstable nucleus by a factor of 10 to the 21st power. Add one more neutron, so that makes helium-7. It's decaying very fast again. We add a fourth neutron, and again it lives for just about a second, because these four neutrons coexist together around this alpha particle. So you see, nuclear processes can be both long and short, and you can't predict it in advance, you have to calculate it. It's a complicated process. And I will finish perhaps with the fastest process, which in general physicists have been able to measure, to study experimentally. This is a cycle of processes, a cascade of processes, which occurs when two nuclei collide at very high energy. The energy is so high that these nuclei move at a speed very close to the speed of light. Because of the fact that they move so close to the speed of light, they also flatten due to relativistic effects, and as they flatten, they collide with each other like two pancakes. And then something very interesting happens. In order to understand what happens, first let me briefly say what the proton is made of. The proton is made up of 3 quarks. This is something that people discovered 60 years ago. These quarks have the name UUD, and this picture, it's even in the school physics textbook, but this picture corresponds to a proton either at rest or moving slowly. If the proton is moving at close to the speed of light, it changes composition. It's a very unusual thing. It's a very strange thing. Yes, what the proton is made of depends on how fast it's traveling. What's more, it depends on what frame of reference we're looking at the proton from. You can even imagine that we have a stationary proton. Here it is standing. We don't touch it. We now just decide to fly by at near light speed and look at this proton from our reference frame. And it turns out that from our reference frame it will already be made up of other objects. What kind of objects? We can imagine that it's made up of this interpenetrating cloud of quarks, antiquarks, and the particles that bind them together, called gluons. These quarks, antiquarks, and gluons, they in principle used to exist inside the proton too, but only they were virtual. They created this cloud of force that held them together. And we didn't count them as a composition. We used to say that we have 3 quarks. Well, they hold together somehow. So, at very high speeds, the cloud becomes a material entity. It becomes a full participant in the composition of the proton. So, at near light speed, we have a whole hodgepodge of quarks, antiquarks of different types, plus gluons that are flying around, and they're all flying together. Now, imagine you have not just one proton, but a nucleus. Each one of them has all this stuff in it. The nucleus flies by at a very high speed. Each of them has clouds of quarks, antiquarks, and gluons, and they start to interact with each other somehow. Basically, you get a mishmash, and the final step is when 2 of these nuclei collide. This mishmash moves slowly within itself. This is a relativistic effect, an effect of the theory of relativity, related to the fact that when you move at a speed close to the speed of light, all your internal processes slow down. So this system here is like a frozen jelly of quarks, antiquarks, and gluons. And now you push these 2 jellies against each other. When you collide them with each other, you don't think you have everything flying apart at once, because it's all happening at close to the speed of light. What do you have going on at that collision? First, these 2 pancakes with this mishmash, which in scientific language is called color glass condensate. It's a kind of jelly-like state. And when these 2 nuclei in the form of flattened pancakes pass through each other, first they are not destroyed, they pass through each other. Just in the space between them there appears some force field, gluon field, which in the form of such tubes binds the 2 nuclei flying through each other. This state is a very unusual state. It's called plasma. It's not even a gas of particles yet. It's not a quark-gluon plasma. It will be later. It's something new, and it appears quite quickly, in fractions of a Yoctosecond, maybe tenths of a Yoctosecond, and it exists for a few Yoctoseconds. Then, when these nuclei have separated, these tubes of the force field begin to evolve themselves. to break up into separate particles. These particles of high energy, these are new quarks, antiquarks, and gluons. And so they give rise to a whole gas, a very hot gas of quarks, antiquarks, and gluons. It's called a quark-gluon plasma, an unusual state of matter that any object will turn into if you heat it to a temperature of 100 trillion degrees. This is the stuff, of course, that cools down quickly, because everything expands, and after a few tens of Yoctoseconds, quarks, antiquarks, and gluons can no longer exist independently. They start to clump into separate particles, protons, antiprotons, something else. And then this gas of particles, which is called hadronic gas, it flies apart. This cascade of processes, you see, starts from tenths, maybe even hundredths of a Yoctosecond. This people are able to track, of course, not directly the evolution in time. They just theoretically calculate how different assumptions about these stages affect the properties of flying particles, like where more particles fly away, or which particles are born more. And then by comparing the predictions theoretically of how it all happened with the results of the experiment, they reconstruct what was happening at that moment. This is probably the fastest thing that people have reliably investigated so far, and the scale is tens of rontoseconds, fractions of a Yoctosecond. We started with ordinary bodies, ordinary everyday phenomena, and gradually going deeper into the depths of time, we inevitably came to smaller and smaller objects. That is, we moved from bodies to individual solid matter, then moved to individual molecules, further to atoms, further to electrons, light, and in general we went deep into atoms to individual elementary particles. It's all inevitable. The shorter timescales you want to study and the more fundamental laws of nature you want to see, the smaller objects you need to investigate. But what's happening on even shorter timescales, we don't know yet. Maybe there's something new there. So far, there are no experimental indications of new processes, but that's probably because we haven't gotten there yet. Sooner or later, we'll get there. That's all for now. Thanks for watching.